Thank you.
Sir.
Thank you. The next welcome speech of our organizing coordinator, Garsten Frank. Please, Professor.
Ah, yeah, okay. Yeah, okay, now it works. Yeah, welcome everyone. I'm very happy that we have so many participants. I think still there are some missing, but okay, hopefully, for example, Roland Dudushava will appear soon to give his lectures. And well, however, I welcome everybody to our summer school. We start with the summer school, and this is already our meeting number 4, I think, if I count the Lübeck meeting in 2017 and the Kiev meeting in 2018, and the conference last year in Samarkand. Yeah? So slowly we know each other quite well, and I think we have many fruitful collaborations, and this is also a possibility to continue with this. Well, at this stage, I think I have to thank many persons. So first of all, the vice rector of Al-Farabi University, Jamilia Aizanova, and the director of the Institute of Mathematics and Mathematical Modeling, Mahmoud Zadibekov, and of course Anna for organizing all these things, and her team, which is so big that I was told I cannot say every name now. Maybe I will do this at the end of the summer school. Thank you very much for organizing these things. And I was very impressed, for example, from the website, very nice. And also the poster, it's really beautiful. Okay, let us thank also our upcoming lecturers of the summer school, Roland Dudushava, Valerie Samoilenko, Jürgen Prestin, Berik Bol, Torobek. We will start with the school in a few minutes. And let me also thank, of course, Al-Farabi University for this wonderful lecture hall and the possibility to be here. Thank you very much, and welcome to everyone. Thank you.
Thank you, Professor. And I'm prepared small presentation for my speech. Good morning for everyone. I would like to welcome all the participants of the conference. Our Institute of Mathematics and Mathematical Modeling is one of the organizers of this conference. Unfortunately, due to renovations, we are unable to host you in our building. I would like to thank Al-Farabi University for supporting our conference. Now we have the opportunity to hold our sessions in such excellent conditions. I would like to express my gratitude to Professor Anar Asanova for the great work she did to organize this conference. Our institute was established 16 years ago. Today, it is a leading scientific organization in our country. In terms of the number of articles published in journals indexed in Web of Science, our institute ranks 6th in Kazakhstan, among all organizations behind only these big universities. And next, следующий страница, пожалуйста. And this table demonstrates you comparison of our institute with mathematical institutes of the former USSR countries based on the number of publication in mathematics field in Web of Science Index. You can see our institute is sixth in this mathematical institutes. And next, please. This table demonstrates you Kazakh mathematics science with 5 and more articles in journal of Web of Science base with impact factor. Yeah. You can see of 16% of actively working Kazakhstan mathematicians are employees of our institute. And for green is our young mathematicians. And you can see in fourth Anar Asano professor as one of leader of publication articles of from Kazakhstan. And welcome to Almaty. Please, next. Wishing the conference success. Thank you. And we have 10 minutes time. We will waiting or begin. Yes. This.
Yeah, also again, welcome. Welcome to the first talk. First talk will be by Jürgen Prestin and will be about polynomial multi-resolution. Please, Jürgen.
So, okay, now, oh, wow. Okay, we want to discuss these spaces Vj, where we have one more sine frequency than cosine frequency, and we want to take the wavelet spaces Wj clearly as the orthogonal difference of these scaling spaces Vj plus 1, orthogonal difference with Vj, and then it is very clear what we mean with frequency localization. It's given by definition of these spaces. So now the next question would be how to define a function which span such a space Wj. Therefore, let's introduce a modified Dirichlet kernel. Dn is a Dirichlet kernel. Dn star is a modified version where we have the highest frequency cosine nx with a factor of 1/2. And here comes an old result of Charles, an old result of Charles Shui and Hrishikesh Maskar from 93, one of the oldest results of such multi-resolution in the periodic setting. In principle, there are almost no older results on the torus up to the French school who said, okay, when we have an orthogonal decomposition, when we have a multi-resolution analysis on the Euclidean space, then we can use Poisson summation formula, and we immediately get also multi-resolution on the torus, but an originally own result on the torus, this is probably the oldest one. To build such a function phi j as given here to span the space Vj, but you see already here's something missing. We want to span Vj not only by one function given here by the integration of this modified Dirichlet kernel, we need also the shifts, but one sentence more on this function. If you look on it, it is the convolution of this Dirichlet kernel against the H function, which is 1 from 0 to pi over n and 0 elsewhere. In principle, this is the Fourier sum of the H function. And this was a basic idea from Hrishikesh Maskar from 93. Okay, and here come the shifts. To take 2n shifts of this function, and then these functions span this Vj, and it is a theorem to show that these shifts are really linear independent and that they span the whole polynomial space given there with Vj. Okay, for the W space, you have to work a little bit more. You have to take the difference of these modified Dirichlet kernels, d2n star minus dn star. And again, you take the Fourier sum of the H wavelet. That means, again, you integrate over 0 up to pi over n. And then this function together with its 2n translates will span the whole function Wj. That also means that all these shifts of this function psi j are linearly independent and they span this space Wj. Okay, that means we do not want to go into the proof of this particular example here, the original first example. We want to look a little bit on more general situations, which also would give a proof of this theorem here in this way. We go to some basics. Okay, the basics here clearly, if we do Fourier analysis, is clearly the Fourier matrix. Very important. It's a basic thing for discussing fast Fourier algorithms and so on. And related to this Fourier matrix is a discrete Fourier transform of length n. Please remind capital N is again a power of 2, which simplifies life a lot then. And we get out of the sequence AK, we get some AK tilde. in the classical way. And this discrete Fourier transform is nothing more than the multiplication with the classical Fourier matrix. That means everything can be understood here as a multiplication with Fourier matrices. Also very important for us if we want to discuss shifts of functions as a circulant matrix. The circulant matrix is one vector of length n, and then you shift the entries of this vector by one and put this as second, third, and fourth row, and so on. This is called a circulant matrix. And it is also very basic for applications of the theory that you can do the multiplication with the circulant matrix in a very fast way. Namely, you have also only to multiply with Fourier matrices. The multiplication with Fourier matrices can be done in a fast way by n log n operations and not by n squared operations. Insofar, it is a very easy thing to work with circulant matrices, and the eigenvalues are nothing more than the Fourier transform of the generating vector A. Okay, now let's switch to functions on the Hilbert space L2, L2 2 pi, the Hilbert space on the one-dimensional torus. Let's take this notation here, L2 2 pi, classical inner product, classical norm in the second row here, given by this integral. We have the Fourier series in L2 with the Fourier coefficients, very clear. And we have the relationship to the discrete spaces, small L2, where we have also an inner product between two vectors A, B, and given here two vectors from L2 over the integers. We have the norm of these vectors, and we have the well-known famous isomorphism between the function space, capital L2, and the sequence space, small L2. And this is very basic here for our approach, and everything is brought together by Parseval equation and Planck-Charel identity, that we can switch from discussing functions to discussing sequences and vice versa. Okay, next thing, the Gram matrix. Here given for functions systems phi k, where we have n functions, then we build the matrix of the inner products with respect to this. When I see here Gram and when I see the traffic outside in the town, I'm still remember this Danish mathematician Gram lived from 1850 to 1916, and he was also very much involved in administration of the Danish Mathematical Society. And in 1916, he went by walk to a meeting of the Danish Mathematical Society, and he was killed by a bicycle driver in 1916. Already 100 years ago, bicycles were already very, very dangerous. Okay, but let's go on here. Gram matrix is also very important for us because we can link it to the quadratic form A transpose GA in the following way, which is every time non-negative. And immediately we get that if the Gram matrix is the identity, then our function system phi k is an orthonormal system, and the Gram matrix is regular if all the translates are linear independent. That means we have to discuss the regularity of the Gram matrix. Okay, that means if we start with some basis of translates, we can construct an orthogonal, or here in this case at first we can construct a bi-orthogonal basis in the way described here, that all the inner products between the elements of the basis phi k, inner product with elements of the basis with respect to tilde should be the unity matrix, identity matrix, and then this function vector of shifts of phi tilde can be constructed from phi by multiplication with the inverse Gram matrix. Okay, we need a shift operator. That means if we have a function phi, application of capital T gives a shift of phi, and we want to construct our spaces V here as a space of shifts of phi, and everything should be involved in L2 space in the Hilbert space L2 given by the function phi here, and it shifts to build the function space V. Okay, the link between the functions on the one hand and the vectors of coefficients on the other hand is given by the so-called orthogonal splines. The name comes from the mathematicians from Singapore, Ko, Lee, and Tan, who investigated this material also in big detail, and they introduced this name orthogonal spline. Because it is some part and it is orthogonal to each other. You see here we take out of the Fourier series all frequencies with their Fourier coefficients belonging to some coset with respect to n. This is also one of the n parts of the Fourier series of phi. And if we put all them together, if we sum up all these orthogonal splines, then we have the function phi back. And so far, it is the main idea here to split a function phi in these cosets with respect to the number n. Okay, and then we have immediately one lemma. If we want to investigate the span of the translates of phi, the upper line, that is a space V, given by the translates of phi, n translates are given here. And we can immediately say it is the same span as given by these orthogonal splines. The proof is very easy. In the proof, we need only one line by saying that the vector phi in bold, is a vector of the shifts. The shifts of phi are clearly only a multiplication by some exponential. That's the first part here. And in the second part it is then the multiplication of the Fourier matrix with the orthogonal splines. That means these two bases given here in these two span are differing only by the multiplication of the Fourier matrix. The Fourier matrix is regular. We have immediately the case that these spans are the same. Okay, and we have also a corollary in the following way. When we want to investigate the dimension D of the space V, when we start with some function phi, where we do not know what is the dimension, are these shifts linearly independent, or what lower dimension comes out for this space V, then we only have to count these orthogonal splines which are non-zero. That means in which orthogonal splines at least one Fourier coefficient is non-zero. This gives us a dimension D of the space. And clearly it follows again by the same idea from the last lemma that these bases for the corresponding spaces can be described, can be seen as differing only by the Fourier matrix F. Okay, now we want to come to the question when a function psi is in the space V included. That means the space V is a very small space in the Hilbert space L2. It's only of dimension capital N. And so far, if we take a Fourier series of psi, if we know all Fourier coefficients of psi, it's somehow very unlikely that psi is in the space V. We have to have very strong conditions on it. And yes, there are strong conditions that the Fourier coefficients of psi have to be related by the Fourier coefficients of phi for all k from 0 to n-1 and for all integer p. And then psi is such a linear combination. And you see here already the proof. And the proof gives already the idea how to construct these coefficients A here. You write psi as its Fourier series. You replace the Fourier coefficients of psi by the condition 1. And then you put all things together and you end at the last line on the right-hand side with a corresponding linear combination of shifts of phi. That means very simple Fourier analysis to see that you have conditions on the Fourier coefficients to ensure whether a function is in this space or not. Okay, next point, if we want to discuss these decompositions, then restability is a very important fact. And for these finite dimensional spaces, it is very easily described. If you want to have restability given in this two-sided inequality with some coefficient, with some constants capital A and capital B, then A and B is given by these L2 norms of Fourier coefficients, where you have to take the minimum over these terms given there, and B the maximum, and you have an orthogonal basis if A and B are both equal 1. Yeah. Yeah, this, okay, clearly I will come also to the corresponding frame formulas, no, but there you do not have in the middle the function itself here. You have the function in the L2 norm in the corresponding frame formula, which you have in mind and which I will also present in the next slide, in the next talks. There you take the L2 norm of the frame coefficients. There you have only the frame coefficients, and in the frame you have much more elements than the dimension is. No? And in the moment I'm focusing on the basis part, where I try to have every time the same number of shifts where the dimension of the space is. Or in the slide before, I discussed how to prove, how to check whether all the shifts are really linear independent. In your case, you would say, okay, I take a lot of shifts. I take a very fine sampling with a lot of shifts, and I know for sure they cannot be linear independent, but I want to have some frame property. Okay, and here I'm still more in the combinatorial idea of I want to have a basis. I want to have the minimal number of elements involved. Okay, here comes result regarding two spaces. Let's say we have a function phi and a function psi who span space V and space W. And again, a basis, we have to include the property that all shifts are linear independent. And now you want to ask, are these spaces a direct sum? That means if we put all of the 2n shifts together, do we really get a function space of dimension 2n? And here comes the answer. If you write the Fourier coefficients in such a equality for all k and for all p, then the coefficients set ak tilde and bk tilde should be the zero set. That means this can be discussed and also very easily in this way. And the proof is again more or less 2 or 3 lines shifting between the Fourier series and the corresponding Fourier coefficients. here given in this formula, writing down such a linear combination of all these 2n shifts, putting it in terms of frequencies, and you get immediately this leads to the fact that the Fourier coefficients of A and B, the Fourier transformed vector of A and B should be the zero vector. Okay, now let's come to orthogonality and bi-orthogonality. We want to ask whether these spaces V and W are orthogonal to each other. V is spanned by the shifts of phi, W is spanned by the shifts of psi, and the first line gives the answer when these two spaces are orthogonal to each other. You only have to look at the Fourier coefficients, and you have to ensure these capital N many conditions to have orthogonality between these two spaces of dimension n. And the second line gives the answer to the question whether the vector of translates of phi and psi are orthogonal to each other. There is this line of equations. These n equations should be satisfied, and both proofs can be done in one line. On the left-hand side, for the first assumption, you need the zero, and for the second assumption, you need the Kronecker delta symbol. You write then the inner product of the shifts of phi and psi. You use the Planck-Charel formula to come to the Fourier coefficients. You sort the Fourier coefficients by remainders with respect to capital N, and you write it in this way, and you get immediately the answer how this properties on functions of f can be described by their Fourier coefficients. Okay, now let's come to the decomposition, because we want to decompose a given function space Vj plus 1 in another Vj plus the wavelet space Wj. That means we want to split into the corresponding wavelet spaces Wj, and here I've written down in this slide a little bit more general. We start with space U of 2n shifts now. That's U is given by 2n shifts, and let's assume again that we have full dimension. That means all shifts are linear independent. Dimension then is 2n, and we want to decompose the space U into two spaces V and W, where both of the spaces have again dimension n. And clearly the main idea is here, again, we want to have spaces which are spanned by one function and its translates. We do not want to split it in some spaces, but in spaces of one function and its shift. Okay, yeah, that means the question is, do there exist function phi and a function psi in the space U? That means because it's in the space U, we can write them in the following way, so that the shifts are orthogonal to each other. And then you go again into the Fourier coefficients. You see that such a condition have to be satisfied for orthogonality, and then you immediately have the rest of the full freedom of taking A and B coefficients for the to obtain these sets, satisfying only this condition alpha k tilde beta k plus n tilde should be different to alpha k plus n tilde times beta k tilde. This is a condition for orthogonality, and a part of that, you have full freedom to choose the alpha k and beta k to make such a construction. And looking back to our first slide, we want to have somehow localized spaces. Clearly, you will, if the idea is that the function theta is somehow time or space localized, you want to construct the function phi and the function psi, which are also localized in some way. You have the freedom now how to choose localized functions, and that is the freedom how to choose a, s, and alpha s and beta s here as coefficients. Okay, this is a construction idea, how to construct these spaces. And then you come to the question of practical algorithms. You want to split a function into the different spaces. You want to reconstruct it out of their parts. And then you need the following theorem saying you have a basis theta of the big space U, and you have a basis of V given by the function phi and its shifts, and psi and its shifts on the right hand of the first formula on top. And now you have a given function in U, and you want to decompose it into the elements of the basis consisting of phi and psi, or vice versa. You have it in the basis with respect to phi and psi, and you want to get it in with respect to theta. And here again helps the Fourier transform. You can do it in a fast Fourier transform way. If you have a fast algorithm for interchanging the basis elements, and you can do it for all general elements in these spaces. And here you see you go to the Fourier transformed basis elements. These vectors f of n is Fourier transform of length n of the vector phi, Fourier transform of length n applied to vector psi is on the left-hand side, and on the right-hand side you have Fourier transform of length 2n applied to the vector theta, and you have this block matrix of 4 diagonal matrices, which gives a very fast algorithm. That means the whole transformation can be done with n log n operations and not with n squared, which would it be normally here in a given way. And you can also immediately get here the inverse operation, because it's easy to invert this block diagonal matrix in this way. And with the inverse, you see the condition you need, because there you have a denominator alpha k beta k plus n tilde minus alpha k plus n tilde times beta k tilde is in the denominator. And on the slide before, this was the condition that everything is of full dimension. Therefore, you can put this into the denominator here to get these algorithms. So that's I do not will focus too much on this algorithmic part on the future part of the talk, but here you get a flavor how to make algorithms if you want really decompose your given signal into the different wavelet parts, or if you want to put together all wavelets parts back to the original function, or in between you want to make denoising or whatever you want to do with your signal, then you have to apply such algorithms of this kind together with the Fourier matrix. This can be very easily implemented and done. Okay, here are some references. I hope you can read them. It goes back to some papers of Locher, Bazensky, Delvos in the beginning of the 80s, who already discussed trigonometric interpolation by one function and its shift. Before anyone discussed wavelets, there was already the idea to generalize trigonometric interpolation by trigonometric polynomials to some more general, let's say, spline-like functions, and to discuss when this can be done in a unique way, when it is defined, and so on. And they use already these methods of classical Fourier analysis, which I showed you here in this talk. Then there is one paper, Perrier, Bastevant, from the French school, who really discussed already a periodic multi-resolution analysis with these basics, which I told you here, which came out after the famous theory of Malado-Bechy-Meyer, how to do this in the on compact subsets of a torus. And then also in the Russian school, there are papers from Privalov. I will come back only in my last part when we discuss Schauder basis of continuous functions. I will come back to the papers of Privalov. He didn't discuss multi-resolution or wavelets. He only wanted to have a Schauder basis. But he already used the theory behind here to obtain first versions of these Schauder bases. Therefore, he has to be mentioned here. Then there's a paper of Chuy Mascar, and then there are some papers who discuss this general situation of periodic multi-resolution analysis by Plonka-Tasche, by this from Rostock, in Germany from the Singapore people, Ko Li Tan. Also Maria Skopina from St. Petersburg discussed these systems, and as well as Narkovich Ward from College Station in Texas discussed it as well. And then there are some own papers, and here I mentioned also some frame paper, which was also discussed in this way. We will come back later on this. Okay, this was a short introduction of the one-dimensional setting to get you a flavor that in principle it is very easy, probably boring to see how easy it is to work with these wavelets, to have algorithms behind, to work with signals, to make storage or denoising of signals by using such wavelet bases. How easy it is, and we can more focus on the question for which particular application, which particular wavelet function psi is well suited, and which polynomial system one should take, or what else one should want to discuss. Okay, let's come to the multivariate setting. What can be done in the multivariate situation on the d-dimensional torus? There we need something new, but something is very much the same. What you see here is probably very much the same from the beginning of the one-dimensional introduction. But if you see that carefully, here is everything which is in vector now is in boldface. That means X is now from the d-dimensional torus. Therefore, it's given in boldface, but it is the same inner product on the d-dimensional torus. It's the same Fourier series. It's the same Fourier coefficient, Ck of phi. Clearly, K is now a d-dimensional vector from Zd. And you have clearly also the Planck-Charel formula, how to describe the inner product between two functions as a sum of the corresponding Fourier coefficients in the multivariate way. And now again, the same, I repeat myself here, but now it's in the multivariate way. We take shift T of y, and again, the basic idea why it is so easy is in principle here very clearly explained in this formula. A shift of phi is nothing else than the multiplication of the Fourier coefficient by e to the minus chi transposed y here. And here I have to be more careful with the transposed system, because clearly k, y, x are vectors of length d in this multivariate setting. Okay, now we go for arbitrary integer matrices M, regular matrices, integer matrices, and we want to say when such a space V is shift invariant, and we call it M invariant if the shift T of y, and this is in the same space, for all y of some pattern of M, and I have to explain this pattern now. What does it mean, P of M? Because in the multivariate setting, it is not so clear which shifts we should take. In the one-dimensional setting, it was very clear. To make a useful Fourier analysis, we take the equidistant samples of the interval 0 pi. In the multivariate setting, it is not clear at all how to do it if you do not want to repeat only the one-dimensional setting by the tensor product case. Okay, in D equal 1, I said it's very easy. There is nothing is to do. And here is the idea what we want to handle as pattern. These are possible patterns with 32 points, and I have to explain a little bit more in detail how they are constructed. We take this matrix M of integers and regular, and the pattern of M are all y in RD such that my is itself an integer vector. Or you could easily say it's m to the minus 1 applied to z to the d. Then we need also all pattern points which are in the unit square. This is pi of m to get a finite set of points. P of m by itself clearly is an infinite set, and pi of m is a finite set of points, 32 points, the slide before. Clear this is our pattern, and now we need to define the generating group. Oops. Generating group. It doesn't generate. Here it comes. That means we take two vectors h of k, and we want to say when they are in the same coset with respect to m, that means that they differ only by a multiple of m is given there. And this is a generating group of m. If you want to say it very easy, again, it is nothing else than the factor group ZD factored by MZD. And this pattern and this generating group belonging to each other by this mod M operation here, mod I operation. Okay, this is a basic business. What we need in the multivariate setting, this pattern of the matrix M and the generating group of the matrix M. Then we can go to the Smith normal form of the Fourier matrix, which we need in the future. There's a famous Smith normal form that the generating group can be factored by classical cyclic groups with respect to some numbers epsilon 1 up to epsilon d, and these numbers epsilon 1 up to epsilon d come out of this famous Smith normal form from where every matrix M can be factored in such a way as given there with some matrices Q and R of determinant 1. Then you can somehow discuss the generating group by this Smith normal form. There are also nice algorithms how to find out for different matrices M the Smith normal form. And it's very important also to factor the Fourier matrix to get fast algorithms. Everything is behind this approach here. Okay, here this comes by the lemma. We want to introduce now a multivariate Fourier transform. Up to now, we use the one-dimensional Fourier transform. That was very clear how to sort it with respect to the shifts and to the frequencies in a one-dimensional way. There's a clear ordering. Here we have a problem. That means we want to discuss now, in principle, the same entries of this Fourier matrix, e to the minus 2 pi I H transposed M inverse times G. This is a matrix. H and G are vectors. H from the generating group and G from the H from the generating group of M transposed and G of the generating group of M. But there's not natural ordering. That means what we now have to fix, we have to fix some ordering of these elements. Which one is not important? We take one ordering, but that we should now fix over all next slides because we want to construct a matrix. And in a matrix, you need an ordering of this group elements. And then this Fourier matrix can be written as a classical one-dimensional Fourier matrices, tensor product of it, Fourier matrix f epsilon 1 up to f epsilon d. These are here the calligraphic f, the one-dimensional Fourier transforms, and you need some permutation matrices pH and PG, and these depend on how you choose the ordering of the elements of G of the generating group. And then it's very easy. You have immediately fast algorithms for all what we want to do in future by multiplication by this Fourier transform is again an operation of order small m times log small m. And small m is here the determinant of the matrix capital M. That means everything regarding the dimension is a determinant of the matrix capital M of the given matrix. And for instance, we have here also immediately the inverse of this Fourier matrix given by this formula. It is a complex conjugate transpose is the inverse of the Fourier matrix. That makes life very easy if you work with it. Okay, and now I repeat again. You could do the same with Fourier coefficients, which we have done already in the one-dimensional setting. We take a vector A from the generating group of elements of the generating group, and you take the Fourier transform out of it, multiplication with this generalized Fourier matrix for the matrix M. You can investigate the circulant matrix. And again, you have immediately the factorization of the circulant matrix by the Fourier matrix and the diagonal matrix out of the Fourier of the discrete Fourier transform of the vector A in the same way as in the one-dimensional setting, and all the proofs are more or less also tensor product proofs of the one-dimensional setting. Very easy. And now we want to classify the pattern which come from the matrix M. That means you start with a matrix M with regular matrix with determinant small m of integers, and you want to see which kind of pattern do you get. And here is the number of different patterns you can construct. Here probably best seen by an example. If small m is a power of 2, which is clearly, again, very good for multi-resolution, then you can see how many pattern do you get in the two-dimensional setting. If our matrices are 2 by 2, then we have 2 to the j plus 1 minus 1 pattern, and a much larger number of pattern in the case d equal 3. Yeah, d equal 3 is again much more challenging than d equal 2. What one can do there, already the number of patterns is there much more. And you could also see the point if you have such a formula that small n is a determinant of the integer matrix capital N, and you have such divisors, then you get a sub pattern by this formula. P of n is a subset of P of m, and we can look here in the simplest cases for d equal 2 and m equal 2. There are 3 subpatterns, and here are the corresponding matrices, and the corresponding subgroup is a cyclic group of order 2. Here is the same for m equal 4. We have 5 such pattern in this way. For all matrices capital M, 2 by 2 matrices with determinant 4, we come up only with these 5 possible pattern and the corresponding generating groups. And they have also some relationship in between. And let's come back to the slide where I showed you already different pattern of with 32 points in the unit square. And here is a theory behind which matrices M produce these pattern and which generating groups belong to these matrices. But for 32, there are already clearly much more possible pattern available. And it's also an interesting idea if you have a particular application in mind, how to choose an appropriate pattern M to fit your goals which you want to use. Okay, now again, we want to look for the shift invariant spaces given by a function phi and such a matrix M. This is now our notation, V defined by the matrix M and a given function phi, L2 function on the d-dimensional torus. We look now for the corresponding orthogonal splines. Here, these are the orthogonal splines with respect to the coset H. If H of phi, you see this includes all frequencies and Fourier coefficients which belong to the coset H from Gm of t. And then the shift of phi with respect to y is then nothing else than the corresponding sum over all these cosets, this Fourier coefficient here. And this gives you, again, the proof which I showed you already in the one-dimensional setting, that on the left-hand side is a vector of all shifts with respect to M, all possible shifts, y and pi of M, a finite vector of length small m. And on the right-hand side, it's a vector of all orthogonal splines with respect to the generating group of M transposed, H in G of M transposed. And these two bases only differ by the Fourier matrix F of M transposed. Here you can switch between the two bases by this formula. And by this formula, you have immediately also that the space Vm phi can be clearly spanned by all these orthogonal splines in this way. Okay, yeah, then again here the Gram matrix with respect to the shifts T when you have X and Y from the pattern and you look for the corresponding Gram matrix G, then here's the decomposition of the Gram matrix by Fourier matrices and the eigenvalues. Also it's a circular matrix, and as I said, a circular matrix means you have in the middle the corresponding eigenvalues of the circular matrix, and here are the eigenvalues. These are nothing else than these products which come out here of this phi and psi, and you see Planck-Charel formula is behind this proof. It's again only a two-line proof to get it this way. Okay, and out of the first theorem here on this slide, you have immediately a corollary if you ask in general what is the dimension of the space of this translates. As I said, the maximal dimension would be small m, the determinant of the matrix capital M, but it could be smaller if shifts are linearly dependent. And if you really want to count the dimension, you have to count in how many cosets do you have Fourier coefficients which are non-zero. That means you count the number of cosets which are non-zero, and here it is given in the way that you have full dimension if all the cosets include some non-zero Fourier coefficients. Also that by Parseval equation, it means that the sums of the Fourier coefficient absolute value squared is positive. But if you have smaller dimension, then you count the number of cosets where this happens. Okay, yeah, then you can ask again how to construct an orthogonal basis. Also if you have a basis of shifts, where the shifts itself are non-orthogonal to each other, then here comes the answer. If you arrange this basis, or if you change the basis in the way that all these sums are equal to the value of 1 over m for all cosets H, then all your shifts are orthogonal to each other. And here is again the construction, how to start with it. You know your shifts of phi. That means you know the left-hand side, and then on the right-hand side you see the construction how to get orthonormal basis. You have to divide by the square root of this sum. If you know classical wavelet analysis from Dobeschi, then you know this formula. In principle, it's the same way with a classical Fourier transform, square root of it in the denominator. That is a construction principle, how to get orthonormal basis elements of Dobeschi wavelets or so on. Here again, in this torus business, it is the same way. Okay, equivalently written down in this way. That means if you know the Fourier coefficients of phi and you want to construct an orthonormalized basis of your space V, then you have to divide by the sum as written here. For all Fourier coefficients, you have to do this. You stay, it has two components. If you change your Fourier coefficient in this way, you stay in the same space. All elements are in the same space, but then all shifts are orthogonal to each other. Okay, this slide I like very much because it also shows how many further possibilities do you have. Let's take such a function phi and a matrix M, where all the shifts are linearly independent, saying the dimension is determinant of capital M. Then I said this is an orthonormal basis. Also you know the Fourier coefficients of phi, and now you want to construct other bases. Okay, orthonormal basis, you have to divide by the square root of the sum of the squares of the Fourier coefficients. If you want to have a dual basis, you divide only by the sum of the squares, absolute values of the squares. And clearly, these bases exist in any case because we have seen the shifts of phi are linearly independent if and only if these denominator are non-zero. That means you can divide by these elements, you get new bases, you get an orthonormal basis, you get a dual basis if the shifts of phi are linearly independent. And now comes the third one, where it is more difficult, an interpolatory basis. That means now we want to have Lagrange fundamental interpolants. We take our mesh, we take our pattern, and we want to get a basis element where the basis element is 1 at the point 0 and 0 at all the other pattern points. And if you take the shifts of it, then you get Lagrange fundamental functions of interpolation, which are 1 at one point and 0 at all the other points. That means very natural question, how to construct such Lagrange fundamental interpolants if you want to make classical interpolation of given continuous functions forever, or functions of bounded variation you could already use in this way here. And then here's the question how to construct these these Fourier coefficients given by this formula. But here you see now you have to divide by something totally different. You divide by this sum here, and you only know that in all cosets, one of the Fourier coefficients is non-zero. But it could happen that the sum here will be zero again. The 1 plus 1 minus 1 could cancel out, it will be zero. This means you can have a function space V consisting of linearly independent functions phi, full dimension of space, but a certain interpolatory process does not cannot be constructed on this pattern M. That means there are no Lagrange fundamental interpolants. That is in spline theory a famous phenomenon to discuss on which point sets do you get, do there exist spline interpolants, and on which point sets such spline interpolants do not exist. And here it could happen that you have such interpolants, or it could happen that you do not have interpolants on these spaces. This can be seen here on this formula. So I can write this formula only if the denominator is non-zero, clearly. Okay, and probably my time is over, and I think it's a good point here to break, and we will see how we go on the next talk. Thank you very much.
Yeah, thank you, Jürgen, for your very interesting talk. I think I can speak without microphone, right? Yeah. Okay, so we have some minutes time left for questions and discussions. So, are there any questions or remarks? Okay, then we maybe continue the next lecture with questions and remarks. Thank you again, Jürgen.
Okay, thank you very much.
So you can now have a copy question.
10 minutes.
There is still time, take photo.
Please use this microphone. Yes, yes. Okay, good.
Yeah, let us continue with the next lecture. It will be given by Valerie Samolenko from the Institute of Mathematics of Ukraine, in Kiev. We are very happy that you were here. And we will give a talk about asymptotic analysis of systems with a small calculation.
Okay, thank you very much. First of all, I would like to express my gratitude to organizing of the summer school and conference, and especially Jürgen for as coordinator of this project. My talk is devoted to asymptotic analysis of systems with a small perturbation. I would like to tell some words about choice of this topic. As you know, many of you visited Kiev and know that Kiev is famous for his scientific school in nonlinear mechanics and especially in serial asymptotic methods. Another direction that is famous of Kiev school is connected with impulsive system. So in my talk, I will consider these problems. One part will be reflect some definition and main notes from asymptotic analysis, theory of perturbation. The second part will be devoted to the impulsive differential equation with singular perturbation, and the third part will be devoted to soliton type solution of coefficient of system of Korteweg type with variable coefficient. In any of this problem, for all this problem, the common feature is presence of a small parameter. In the first talk, I will be present some history description of the this direction, and will give a main definition and concepts of this theory. And the second part, as I said you, I will consider the first order differential equation with single perturbation and the impulse of action. In this part, we will consider layer function methods and another technique devoted to construction of asymptotic approximate solution, Vishay-Klusteric methods. I'm afraid that I will have not sufficient time to present this technique in detail, so I will introduce you in this technique only in general form, in general frame. So, as I told you before, that the third part of my talk will be devoted to soliton type solution of Korteweg type system. Now, at present, there are different generalization of Korteweg type equation. This equation is very famous because it is one of brilliant example of integrable system. along with the other system. And many researchers consider a system of Korteweg type ones, and they generalize this system into different way. One of the way is connected with direct generalization when the coefficient of this equation became variables. I prepare my presentation with full text for my lecture, so it will be convenient for you to have a hit before myself and maybe for you to read, because maybe my pronunciation in English may be not very well. I know. Okay, I will start with my first part of lecture. Okay, in what direction I must do? Because don't work. Okay. Please help me. Please, next slide, because this device, okay, thank you very much. So, the first remarks will be connected with the following feature of a study on a linear system. As you know, to find exact solution is very difficult, and sometimes it is impossible to find exact solution, a solution in exact form. This is the first moment. The another point is that sometimes you have an exact solution, but it is very difficult to imagine what this exact solution may be present on the graphic, or what properties has this solution. Every you imaged very well such function as power function, sine, cosine function, but it is more difficult to imagine what the graph is, for example, Bessel function. It is only for some example, for explanation why sometimes it is useful to use some asymptotical expansions. The asymptotic methods are known for the ancient time. At least in this connection, it is useful to remember a paper by studies by Lagrange, and I want to tell you that Lagrange study developed some asymptotic techniques and applied these techniques in theory of celestial mechanics. At the time when Lagrange studied some problems with small parameter or small perturbation, expansion will perform in formal way. Nobody study the problem of convergence, this expansion, and nobody ask about justification of these asymptotic methods. So maybe historically, it is very famous example connected with estimation of integrable. So as you see on these slides, Euler considered the integral of the form in the form number 1, and he estimate this integral for large positive value of z. And he do his calculation in formal way. He consider fraction under integral, represent this fraction as infinite geometrical progression in form 2, and later substitute this expansion into integral. Later he integrate this series, despite of this series is disconnected, divergence of the lot in interval, and is converged only on a central interval. Every student can write a condition under which the integral 3 can be calculated, or series sequence 2 is convergent. Later he perform integration by part and obtain the general terms for asymptotic expansion for the integral in the form of 5. Okay. It is easy to see that in the asymptotic series 5 is divergence, because the general term, as you see at the first row, will tend to infinitely as number of terms tends to infinitely. But in the other other side, in the special sense, this expansion give good approximation for the integral. What it means? It means that, please look at the formulas below. If you consider difference between function f and particular sum of this series, you can calculate that this difference is expressed by fraction that tends to 0 as variable z tends to infinitely. This conclusion follow from representation of fraction into two parts. The first part corresponds the particular part of series, and the other part correspond the remainder of this series. Please, next slide. So, in the previous example, we consider the first example of convergence series that this not convergent, this version series. In this sense, this series is asymptotic. What it means? That this series is not convergent, but in some sense, this series give good possibility for approximation what value we consider. The next example is connected with solution of ordinary differential equation number 6, and we construct some approximate solution of this equation in the form by formula presented by formula 7, and if we do formal calculation according usual rules, we obtain relation from which, according to general idea of asymptotic expansion, we obtain some recurrent relation from which we can obtain the coefficient of expansion 7. Again, as in previous example, we obtain series that is divergent for all x, because except 0, because x is positive. So we obtain formula 9 for approximate solution of equation 6. Now, please, next slide, we discuss the problem about approximation of and divergence of this series. If we consider relation of two terms of this series, we obtain that this relation tends, as previous in previous example, to infinitely. So this series 9 also diverse, but for numerical calculation, it is very useful to use this representation of solution of equation 6 in the form of 9. Really, we can deduce the exact solution of the equation 6. At the slide, you can see simple calculation. If you calculate left and right side of this equation by exponent x, you obtain some relation. Later, from this formula, by integration, you obtain the exact solution. So, if you later, next step, calculate this integral by calculation by part, you obtain some part of previous series and remainder in the form on the last row of this slide. Please, next. So we have remainder in the form Rn of x. At the first point of view, it is very large values, but it is not the same. If we calculate and estimate this remainder from the formula 10, you see that this remainder tends to 0 as independent x tends minus infinitely. So what we see, we have that constructed solution are asymptotical in sense that this serious divergence, but when independent values tends to, as in this example, to minus infinity, the remainder tends to 0. So the particular sum of the series presents good approximation for the value under consideration. Now we will consider the next form of asymptotic expansion. The first two examples present expansion in independent values, and this expansion for Diophant equation or Diophant oscillator presents asymptotic expansion in small parameter. First of all, it is should be mentioned that equation is connected with the name of German engineer inventor Georg Wilhelm Christian Caspar Diophant. He proposed this equation and study his property. This equation is very interesting because if you consider this equation with external influence, particular, for example, periodic instant, this equation possesses demonstrate chaotic behavior. But here we consider equation without external influence, without perturbation in time, in this simple form of 18. And first of all, we fulfill some rescaling of independent and dependent variables and come to the equation with small parameter. Please, next slide. Okay, not much. Okay. Yes. Okay. So if you use this notation, x with point and x with 2 points for second derivative, we by special rescaling, this rescaling is presented on this slide before equation 12. We obtain Diophant equation with small parameter. I would like also to mention, to recall that Diophant equation describe oscillator of mass attached to a nonlinear spring and a linear damper. The restarting force provided by the nonlinear spring is given by formula. You see cubic nonlinearity. So in such way, small parameter is introduced into the equation, and now it is possible to find asymptotic solution of Diophant equation number 12 with small parameter. Okay, good. First of all, I would like to note that Diophant equation has first integral, the value that is constant over this exact solution of Diophant equation. It is very useful remarks because it means that any solution of Diophant equation is bounded. So we will seek asymptotic solution of Diophant equation in form of 12, in the form of power series, in epsilon in small parameter with initial condition. This initial condition means that we know some initial amplitude of x and the velocity of this point is 0. So to perform all necessary calculation, we must to represent the right side of this equation 12 at the previous slide in the form of expansion in small parameter. This simple calculation and we in such way obtain a system of first of all we obtain relation which contain series in small parameter, and we later equate terms near the same power of small parameter. It is usual idea of perturbation theory It is the same to idea when two polynomial are equal, the two polynomial of the same degree are equal only if their coefficients are correspondingly equal. It's the same idea works here. So we find the first approximation x0 of t, and the next approximation, the first term, is the solution of the problem with non-homogeneous equation of second order with zero or trivial initial condition. It is easy to find exact solution of this equation, and we can continue this procedure so much so we like, but except tedious calculation, we will have no more new information. These two first terms present us some information that are very useful for us. First of all, you see that the function x it is must be x sub 1, not x sub 2. So in such way, we obtain the approximate solution of differential equation in the form 15. First of all, I would like to attract your attention to the 2 points. We reduce nonlinear problem to infinite set of linear problem. It is a specific feature of asymptotic methods in general, and especially for regular system, because when we will consider singular perturbed system, at the first step we may have nonlinear problem, but for regular perturbed system, usually, frequently or every time we have reduction of nonlinear problem to infinite set of linear problem. So it is the good possibility to simplify the initial problem. But we must pay for this simplification. And this payment is connected with the form of asymptotic solution. As you see in formula 15, there are some terms connected containing a power of independent time t. And in the next approximation will be t in power of 2, next will be contained t in power z, and so on. These terms are called secular terms, and they influence badly on convergence of this series. So for general case, we obtain again approximate solution, but this series that gives approximate solution diverge in as usual series. In this connection, I would like to recall two techniques which allow to construct asymptotic solution for system like Dufin, like van der Pol, or other system of oscillatory type without secular terms. One technique was proposed by Lindstedt and Poincaré, and another technique was proposed by Krylov and Boglubov, and later was developed by Metropoolsky. Now, at present, it calls as Krylov, it refers to as Krylov, Boglubov, Metropoolsky methods. So, another point what I would like to do is the following. So, what way we can estimate the suitability of constructed solution? First of all, we can consider difference between exact solution and constructed solution, or consider the values which we want to approximate and the constructed approximation for these values. But there is another possibility to estimate the suitability of constructed solution. For example, if some system has a first integral, as in this example of Dufin system, you can use this first integral for compare of exact and approximate solution. You can draw a face portrait in face plane for this exact and construct the solution, and later compare the difference between line for this solution. So if you perform this comparison of exact and constructed solution for these two kind of solution, especially for solution constructed by Krylov-Boglov-Metropolsky technique, you will see that accuracy of constructed solution is very well. So we move further. So we consider some example of problem from different fields of mathematics, pure mathematics, applied mathematics, and we can see that we can construct some approximate solution as asymptotic series, but this series diverge. But in some sense, this series present good approximation for values what we consider. So, but it is first point. The another point is connected with notion of function. In the frame of string axiomatic framework of mathematics in 19th century, this kind of solution was unusual because any function do not correspond such kind of solution. So, but on the other hand, it is necessary to remind a notable example connected with discovery of planet Uranus. Uranus, what that was discovered, as it is right, at the tip of a pen. It was due after some calculation and after some observation, application of this calculation for observation of celestial. So it was some paradox or absurd situation, and this problem must have to be solved. This problem was solved at the end of 19th centuries. First of all, it is necessary to recall the fundamental monograph of Henri Poincaré, who and his monograph, New Methods of Celestial Mechanics. This book was printed during 5 years, and this book played a very important role in creation of theoretical foundation of the theory of asymptotic methods. And another recognition, these methods were received at the end of 19th century when Paris Academy of Science announced a competition under title Investigation of the Increasing Role of Divergence Series in Analysis. The winner of this competition was the French mathematician Émile Borel, who studied different kind of divergent series in calculus, mathematical analysis. So in such way, he presents some paper in which asymptotic methods receive some justification, and in such manner, new direction in mathematics, or maybe in mathematical analysis and applied mathematics, was formed. Now it is known as asymptotic methods or asymptotical analysis. At present, asymptotical analysis is one of many important methods for studying nonlinear problem in various fields of modern science and its application. First of all, in applied mathematics and physics. Below, the main attention will be paid to consideration of expansion with respect to a small parameter. such parameter can may already be present in the problem or may be introduced in some way. Example of introducing a small parameter was given when we consider Dufin equation. Okay. Now I proceed to presentation of some notation and some definition from asymptotic analysis. I begin from symbol O small. It is well known to every student of university. This symbol means that if two function, for example, f of epsilon and g of epsilon is in connection or small, it means that for any positive delta which is independent of epsilon, there exists epsilon 0 such that for all epsilon between 0 and epsilon 0, we will have the following relation. This relation is holds. So the last condition we can write also in the form of using the limit or in other notation. Some examples are given on the bottom on this slide. So you can see that sinus 1, for example, is O small of 1 because when small parameter tends to 0, sinus of epsilon tends to 0 also. So this condition of definition of this symbol is fulfilled. The other also simple example can be easy calculated when you use Taylor series for function cosine in second set example or for function sinus, and when you do some sufficient quite simple calculation, we obtain this result. The last is more complicated example. For the first time, maybe it seems because it is necessary to consider limit of relation epsilon power n and a logarithm. But if you use some rules, especially L'Hopital rules, you easily calculate that this relation is true. So the another notion is connected with uniformly performance of this relation. If function f and g depends additionally in the space variable, as in this slide, we said that this relation is uniform if the corresponding relation fulfilled uniformly with respect to variable x. So at this example below, you see some example of this value which are uniformly and non-uniformly related one to each other. Okay, the next definition is connected with symbol O large. We use this notation for two values, for two, I can say, two function f and g. So this notation means that the function f and g are in this location if this relation, if there exists a positive constant a independent of small parameter and value epsilon 0, such that for all epsilon from corresponding interval, the inequality holds. We also can write this notation in form of limit or inequality presented on the slide. So as it is necessary to note that this relation reflects relative property this function with respect one to another function. So here you can see some example of such function possessing such properties. So you can easy to verify validity of this relation, and it is also a need to use Taylor expansion for correspondent function, and you can see you can easy to calculate and prove this relation. Okay, the next relation, the next definition connected with uniform or relation. So two functions fx of x and epsilon and gx of epsilon are connected, are related with relation or relation uniformly if exists some constant a which is not dependent of independent variable x and small parameter epsilon evidently, and this inequality holds. We can formulate this property in other ways. It means that the bound of function f(x) relatively to function g is uniformly across the domain M, and the constant a and epsilon sub 0 do not depend of x from some set, and you see some example of fulfilling this relation. Now, we consider scaling function. Above, we consider some example of expansion in small parameter. We do this expansion in power of small parameter, but in asymptotic analysis, there are used another scale function, and this example, the example of this scale function is given as example. In general, we consider arbitrary set of delta sub n of epsilon function, but this function must satisfy relation on the second from the bottom of the slide. Delta O n is O small of delta n minus 1. This sequence is called asymptotic sequence, and in mathematical model, under consideration of different problem, there are different scaling function used, and particularly the more used function are presented at this slide. Asymptotic series is a specific example of asymptotic expansion. We will consider this point the next slide later. So, general form of asymptotic expansion. So, in general, a sum of such kind is a asymptotic expansion. Here we use general asymptotic sequence, and for representations that this function, this sum is representation of some function, we use some notation like this slide. It means that we consider this notation as small parameter tends to 0. It is obligate condition for consideration of similar relation. It means that this relation means that asymptotic relation for or representation of function f of epsilon with remainder that is O big from delta n, the first term that we neglected can be considered. So if we consider representation function in the form of asymptotic expansion, we must remark that such representation is not unique. Why this representation is not unique? Because you can use different system of asymptotic sequence. But if you have given asymptotic sequence, in this case, representation function by asymptotic expansion is unique. A special slide is devoted to definition of asymptotic series in the sense of Poincaré. So, asymptotic series presented on this slide is called an asymptotic series for the function f epsilon as epsilon tends to 0, accordingly Poincaré, if for any natural n the relation holds. So we consider we have limit when small parameter tends to 0, and we consider difference between function and particular sum of this asymptotic series. If this condition holds, so we have a series that is called asymptotic series in sense of Poincaré. Now we proceed to the next notation which is connected with uniformly suitable and non-uniformly suitable asymptotic expansion. Usually we use asymptotic expansion for solution of different problems, especially differential equation, ordinary, both ordinary. Это не я. It is not me, sorry. Okay, we usually use asymptotic expansion for solution of different problems for ordinary and partial differential equation, for integral equation, for integral differential equation, and other problem with small parameter and some space variables. So in this case, we obtain some asymptotic expansion for value which depends on space variable and small parameter. So for estimation, it is very important to know is uniform, this is difference uniform or not with respect to the given, for example, variable, space variable. So we said that this relation is asymptotically suitable. Asymptotic expansion is uniformly suitable if remainder of asymptotic expansion is small, is correspondent value of terms of asymptotic sequence uniformly. Like, so the condition on the last condition of this slide is fulfilled. So now we consider the simplest arithmetic operation on asymptotic expansion. When we consider some differential equation, we have different power of independent value or more complicated, more general, some nonlinearity. In this case, we must represent right side function of the equation as series in small parameter. In this case, we need to calculate some difference multiplication or do some main operation over asymptotic series. So the two arithmetic operation like addition and subtraction is very simple. If you have two asymptotic series, the linear combination of this asymptotic series is defined in usual way. If you consider asymptotic linear combination, you obtain also asymptotic combination of correspondent asymptotic expansion. More complicated problem is in the case of multiplication or division of asymptotic series. This problem is connected with the following point. If you have some asymptotic sequence, for example, consisting of function delta sub n, while multiplying to asymptotic series, you may obtain multiplication to terms of this asymptotic sequence. But the given asymptotic sequence may not contain the product of these two terms. So in this case, it is impossible to represent multiplication of two asymptotic series as asymptotic series. But in particular case, when elements when we consider as elements of asymptotic series power of epsilon, we can define product of this asymptotic series very easy. The result is presented on the bottom of the slide, and you see that production of two asymptotic series will be given also as asymptotic series with coefficient calculated according to simple rule. So now we proceed to consideration of regular and singular perturb systems. Regular and singular perturb system. In perturbation theory, there are considered two different types of problem: regular and singular perturbed problems. Regular problems, regularly perturbed problems is characterized by the formula properties. If you put small parameter equals to 0, you obtain unperturbed problems. And in this case, the space of solution of perturbed problem and unperturbed problem have the same dimension. Same dimension may be the same set of solution, maybe. In contrast, in case of singular perturbed problem, when the parameter is 0, we obtain some problem is a problem of different type as previous or given problem. And in this case, in the case of singular perturbed problem, the space of a solution of unperturbed problem is less than the set of solution of perturbed problem. Now we consider difference of this, first of all, example of some problem with regular perturbation and with singular perturbation. This equation, van der Poel equation, Dufin equation, and quadratic algebraic equation present example of regular perturbed problems or problems with regular perturbation. The other problem, for example, this slide, you can see two examples of problem with singular perturbation. As you can see, if you, in the second order differential equation, put small parameter to 0, we obtain the first order differential equation. When small parameter is not equal to 0, you have second order differential equation. Of course, the second order differential equation has more rich set of solutions than the first order differential equation. In this case, when you have the first order differential equation without independent variable time, you know that the first order differential equation have not periodical solution, but you know that the second order differential equation in autonomous case has periodical solution. So we have such qualitative difference between singular and singular perturbed problem and unperturbed problem. And another interesting example connected with simple algebraic second order differential quadratic equation denoted by formula 19. Now we consider some exact solution, some problem with exact solution, and do comparison of exact and approximate solution, solution constructed with technique of asymptotic methods using the direct asymptotic expansion as below for Dufin equation. So, okay, I wait, maybe somebody reads this slide. Okay, so it is very simple calculation. So we consider a quadratic algebraic equation. It is very easy to find exact solution. These final solutions are denoted by x sub plus, x sub minus. It is convenient to denote this solution in the following way. So if we use Taylor expansion for the square root function, this expansion for your convenience is given here. We obtain approximation for exact solution, which we obtain by usual way. We take exact solution and do expansion using Taylor formula. Next way, next method or next way we will do now is the following. We seek equation, asymptotic equation or algebraic equation in the form of asymptotic series. It will be given on this slide. We calculate previously the second power of this series. Later we substitute these values into equation, equate the coefficient near the same power of epsilon, and we obtain the coefficient of this asymptotic solution. We have two possibilities for the main coefficient A sub 0. It equal plus or 1 or minus 1. Later we find the second terms and the third terms and so on. And we obtain asymptotic solution for quadratic equation with regular perturbation in the form of this solution. It is the same solution as before. It is the same. So it is very well, very fine, because we, in this particular case, very simple case, we obtain the exact solution, but the solution obtained after expansion using Taylor formula. A more complicated case is connected with singular perturbed algebraic quadratic equation. We consider equations 22. We find two exact solutions. If small parameter is not equals to 0, we have two equations. If small parameter equals to 0, for perturbed case, unperturbed case equation, we obtain one exact solution, x equal ratio 1 and 2. And now we seek for solution of equations 22 in form of asymptotic series 23. We substitute this series into equation. We perform simple calculation, and as before, we find that this solution have only this coefficient, the last equation on this slide, will be present only one solution. What is a problem? A problem is that perturbed equation has two solutions, but by asymptotic method we construct only one solution. And the question is, where does the second solution disappear? It is very interesting question, but it has very simple answer. And the asymptotic solution, when we calculate exact formula for solution or algebraic solution and expand square root function, we obtain two formula. You see that solution x plus tends, when 0 tends to 0, tends to exact solution of unperturbed problem, and other solution x minus tends to minus 0. So in this case, for singular perturbed problem, the second solution go to infinity. So goes to infinity. This situation is very characteristic for singular perturbed problems. First of all, when we consider asymptotic solution for a singular perturbed problem, we consider specific particular solution which tends to some solution of unperturbed problem. First of all, some solution of perturbed problem may disappear, and this phenomena is typical for singular perturbed problems. So when perturbation parameter tends to 0, the property of equation may be changed, and this equation may have different properties of solution. At the last, I present some reference. First of all, I want to tell you that the main books you can find in Russian in internet. It was translated in Moscow, and the second book is also useful for study of nonlinear partial differential equation of hydrodynamic types, for example. And the last slide. Щиро дякую за увагу.
I think we have some time for questions and remarks. Are there any questions or remarks? Then we keep it for the next time. We close the session now and we see each other again at 3 o'clock. Yeah? And let us thank the speaker again.